The requirements from College Board for what you need to know about the separation of solutions and mixtures is incredibly chillax, and I'm quite positive you will get bored while watching this video. Today, I'm going to walk through the most common types of lab procedures when we are separating solutions and mixtures. The only thing that's going to be expected from you is to know what chemical or physical properties we are exploiting in order to separate our substances, and you also need to be familiar with the names of the most common types of separation processes. You don't have to memorize any procedures yet or exact quantitative data. Let's begin. When we want to separate solids from a liquid based on their particle size, we use filtration. Filtration is a physical way of separating our solutions. Filtration only works well if one component is insoluble, such as sand and water. I'm sure you know how filtration works, but imagine here we have sand and water mixed together. If we run this solution through our filter, the sand will stay stuck in the filter, and what comes out will be fresh water. And it'll be only water, there will be no sand in it because it'll be stuck in the filter. But so like I said, this is only going to work if we have an insoluble component such as sand. To make filtration more effective in separating dissolved substances, we can form a precipitate. That's when we combine ions with one another to form an insoluble solid that we can then filter out. For instance, if we have a solution of aqueous silver nitrate, but we want to pull out all of our silver from this solution, we can combine this aqueous silver nitrate with excess aqueous NaCl. We will then form solid silver chloride, which is our precipitate, which we can filter out of the solution, because it's a solid, it won't dissolve. So that's one way we can increase the effectiveness of filtration. We can also use a technique known as recrystallization. In recrystallization, we start by taking a solid and adding a lot of heat to let it dissolve and form a solution. Once we have our solution, we let it cool back down, and after it's cool, our solid will reform. This reformed crystal will have less impurities in it, as the impurities will stay in the solution. That's what recrystallization is. We can then filter out our increased purity crystals and collect them. Both recrystallization and forming a precipitate are ways we can expand on the capabilities of filtration. Distillation separates mixtures based on boiling points, and it is a physical form of separation. For instance, water and ethanol will mix with one another since they're both polar, and we obviously couldn't just filter out the ethanol molecule by running this through filter paper. But the boiling point of ethanol is much lower than water. Ethanol has a boiling point of 78.4 degrees Celsius, and water has a boiling point of 100 degrees Celsius. So if we take our mixture of ethanol and water, and we raise its temperature to slightly above the boiling point of ethanol, then our ethanol will begin to evaporate, but not our water. Only the ethanol will evaporate. The ethanol will go up this tube, and it'll run into something called a condenser. Our condenser is like a tube inside of a tube. In the inside tube, our ethanol vapor flows. But the outside tube, this blue part over here, has cold water constantly running through it. And so the cold water will allow our ethanol vapor to turn into ethanol liquid. This liquid will then flow out into our collection point. And so using distillation, we can distill out all of our ethanol while leaving only water in our original solution. Fractional distillation is like this, but we introduce something called a fractional column into our setup. This fractional column will allow us to separate mixtures with boiling points much closer to one another. Our fractional column creates repeated condensation and vaporization cycles as the liquid moves up the column, which creates a temperature gradient and enriches the vapor with the lowest boiling point as it moves up. You'll recognize this image from the first slide, but this is also how we distill crude oil. There's a lot of different parts. We've got fuel, diesel, kerosene, petrol, butane, and propane, and each one of them have different boiling points. So we introduce a fractional column into our distillation, and as you can see, we create a temperature gradient here, and as we move up the temperature gradient, we distill different components from crude oil. Also notice, at the very top of our temperature gradient is the substance with the lowest boiling point. That's how fractional distillation works. Next up is solvent extraction. Solvent extraction separates mixtures based on their solubility and polarity. Imagine that in this beaker, I have this yellow-colored mixture. It's made up of two components, and I want to separate them from one another. In a solvent extraction, we would add another solvent into this mixture. Let's say a red solvent. We would just pour some of that solvent into our solution. We would then mix this vigorously, and after our solution settles, we would form two distinct layers. This is what you can see happening here in our solvent extraction. We could then separate these two layers through something like this separatory funnel here. How come we're forming two different layers? Our second solvent is immiscible with the first solvent in our solution. The component we want to separate from our original solution will dissolve better in the new solvent. So when the mixture settles, the component we want will separate into the new solvent and form a new solution. This new solution will not mix with the original one, and that's why we form layers. And of course, after you have the two layers, you just separate them through a separatory funnel. Lastly, we have chromatography. Chromatography separates solutions based on their polarity, and it's probably the most complex out of all of them. Let me walk you through chromatography very carefully. Imagine that I take a bowl and I mix in some paprika oleo resins, which I'm going to abbreviate as PO, and also some yellow 5. I'm going to mix these two in my bowl and I'm going to form orange. Both of these are food coloring agents used in everyday life. This is the stuff in your food. Paprika oleo resins is red and yellow 5 is yellow. Importantly, however, PO is non-polar and yellow 5 is polar. So I've created an orange food coloring by mixing these two agents. Now I'm going to take some of this orange food coloring and I'm going to put a blotch of it on a piece of paper. How could I turn my orange coloring back into red and yellow? I obviously can't distill it. I obviously can't run it through filter paper. So to do this, we're going to use paper chromatography, which again separates solutions based on polarity. I'm going to take my paper and put it in an empty beaker. I'm then going to fill the bottom of my beaker with acetone. You know acetone as the active ingredient in nail polish remover. It has that really toxic smell. Importantly, acetone is polar. As the acetone molecules get absorbed by the paper, so the paper becomes wet with acetone, and it moves up the paper, both our nonpolar PO and our polar yellow 5 molecules will be attracted to the acetone molecules. They will be attracted because of intermolecular forces of attraction. However, and this is super important to realize, because yellow 5 is polar, it will be more attracted to the acetone molecules than PO will be. And so, because it's more attracted as the acetone molecules move up the paper, making it more wet, our yellow 5 will also move up the paper. Let's say that our yellow 5 follows the acetone up to here. And it is more attractive than the PO, so it will move further than the PO. The PO will stop somewhere around there, because again, yellow 5 is more attracted than our PO is. I hope that made sense. An important note, on the AP exam, they're usually just going to give you a generic polar versus nonpolar component rather than specific dyes. I just felt like it would make more sense and entertaining to do it with actual colors. Let's also provide some terminology for this process. Our paper is known as the stationary phase. Pretty simple to remember because it doesn't move. Our acetone is known as the mobile phase. It's also known as our solvent. Our acetone will only creep a certain distance up the paper. Let's say that it stops right around here. Where it stops is known as the solvent front. And lastly, our retention factor is the distance traveled by one of our components. So that's either our PO or our yellow 5. And this is divided by the distance traveled by our solvent. So it's the ratio between the distance one of our colors is traveling, or one of our polar or nonpolar molecules is traveling, divided by the distance of our solvent front. There are also other types of chromatography, such as column chromatography and gas chromatography. But the basic idea is always the same. We are separating components based on differences in polarity. And make sure you know this definition. Chromatography will separate a solution into its components based on the polarity of the components. And with that being said, that's everything you need to know about the separation of solutions and mixtures in chemistry. Again, just make sure you are familiar with the different processes, but don't worry about remembering the exact steps for each or the materials needed to conduct them. If any of this was unclear, I recommend rewatching parts of the video. If you're still stumped, take a break and come back after. Thank you for watching.